Okay, so this video is a little bit of an odd duck in that we're not going to be solving any differential equations and we're not going to do any complex numbers. We're going to do some trigonometry, some trig, and it will help us a great deal if we can get a little bit of trig down. I should say we are going to be using some complex numbers in this discussion, so if you have not seen or if you're not familiar with the complex numbers, you might go back to the complex number video and check that out. All right, so just to begin, let's talk about just a basic waveform. And you could use sine or cosine for your basic waveform. I think I'm going to use a cosine function, and we'll see why that would be later. But if I have the function a times the cosine of omega t minus delta, the question is what do these three numbers represent in terms of the graph? I seem to be writing kind of sideways there. This is my normal cosine function, right? With a period of 2 pi. And so if I multiply that by a, I know that that's going to stretch it. And so the a is said to be the amplitude of your wave, right? The omega here is going to be the number that we use to determine the period of your function. And the period, you might remember, the period is the length at which the pattern starts to repeat itself, or you could think of it as the length of one cycle. So the period is the length for one cycle, and the period is defined to be 2 pi divided by omega. So that's length for one cycle of the wave. Okay, now I should say frequency is the other measure that we use, and frequency is what is the frequency? Well, the frequency is defined to be 1 over the period. 1 over the period. And so you could see here, if this is, length per cycle, then frequency would be cycles per length. So you could think of this as cycles per unit length, whatever your length is. It might be in meters, might be in whatever. Okay, so in other words, the frequency is going to be 2 pi, omega over 2 pi. Now I should also say that there is something called circular frequency. And the circular frequency is used so physicists don't have to divide by 2 pi. They're lazy that way. Circular frequency is just going to be the omega. Okay, and so that is kind of easy to pick off of the wave, right? So if you're looking at the wave a times cosine omega t minus delta, it's easy to just pick off the circular frequency as omega. Good. And then finally, the delta. Now there's two ways of thinking about the delta. So just like the omega is not the period itself, we have to do a computation with the omega to get the period. The delta is going to be used for the phase shift, for a shift in the graph, but the delta itself does not represent the units of the shift, right? And I wonder why that would be. So just as a side note, remember what the difference is between f of x and the graph of f of x minus c? So to get the graph of f of x minus c, you would shift f of x, c units, to the right, right? And how would you get the graph of f of 2x from f of x? To get this graph, you would shrink, or it's the way to think about it is you're multiplying the x-axis by 2, you're stretching the x-axis, but the graph stays the same. And so it looks like the graph is actually shrunk this way by 1/2. So this is shrinking the graph horizontally by 1/2. Okay, so now the question is, what do you do if you have f of 2x minus c? Well, the order of operations here is really important. So what you want to do is, I think the best way to do it is to factor the two out. So take f of 2 times x minus c, right? And now you can see what the, c over 2. And now you can see what the order of operations is, right? So you would take your x, you would shift it forward by c over 2, and then you would shrink by 1/2, okay? So the order of operations here is important. We're normally lazy in not putting the t minus something in parentheses. To actually graph this function, you would need to do that. And so the upshot of all of this side note is that the actual phase shift itself of your wave, can you guess now? It's not delta itself, it's actually delta over omega. Right, so that's how much you would actually shift the wave forward. Okay, so let's do an example. So let's see if we can graph 3 times the cosine of pi t plus pi over 2. Okay, and the idea is you want to start with the graph of the cosine and then work your way out from there. So let's see. The cosine function looks like that, right? Multiplying by 3, of course, extends it this way. Let's see, I'm going to go ahead and write that. 3 cosine of pi times t plus 1/2. Okay, and so let's see. My phase shift then, oh, by the way, what's the period? The period's going to be 2 pi over pi, which is 2. And I'm going to shift forward by 1/2, right? Oops, sorry. I'm going to be shifting left by halves. Not by halves, 1/2. Let's see if I get that together. So if this is a period of 2, where's 1/2? 1 is there. 1/2 would be this much, right? So this is going to end up at the origin. Oops, I'm running off my page. And so my graph is going to look like, I'm going to go ahead and expand my graph now. Right, so this is going to be where's the end of the cycle? Right there. So that's going to be 2 units, 1 and 0, and then my graph continues out this way. And so this goes between plus or minus 3. Right? Good. All right. So that's what the graph looks like of 3 cosine pi t plus 1/2. Good. Okay, I'm going to pause this and get ready for another example. Okay, so I want to talk about the cosine sum formula for our second example, cosine sum formula. And so actually we're going to be using the difference, but that's okay. Cosine of x minus y is equal to, anybody remember? Cosine of x, cosine of y, plus sine of x, sine of y. Now, it's kind of fun to think about this in terms of the complex number system, because this is the real part. Note, cosine of x minus y plus I times sine of x minus y is equal to e to the I times x minus y, right? And so here you can get both the imaginary part and the real part together as the exponential function. Why would you do that? This is e to the ix times e to the minus iy, and that is cosine x plus I sine y times cosine of x. I'm going to go ahead and bring in the negative sign as the conjugate, right? We showed that before because cosine is even, sine is odd. Good. And then if you multiply all of this out, oops, I messed that up. That's I was going to say that all cancels out. This is cosine y and sine y. Good. Okay, so if you were to actually expand this out, what you end up getting is cosine x cosine y plus sine x sine y for the real part. I should let you do that. So multiply this out to see that we get the formulas for cosine x minus y and sine of x minus y. I don't want to do that here because it's just some algebra and it loses its entertainment value. Okay, so I want to say using the cosine sum formula using the cosine sum formula, we can prove the following results. If you take r times cosine of omega t minus delta, that's equal to r cosine of delta times cosine of omega t plus r sine of delta times sine of omega t. Right, so what I'm doing is I'm using the cosine sum formula there, right? So here I've got the minus, I've got the plus there. And so the idea here is that I think you can see here now that the formula that I want to get to is that if I have a cosine of omega t plus b sine of omega t, then I can rewrite that as r cosine of omega t minus delta, where r equals the square root of a squared plus b squared, and theta is the argument of a plus ib, or to just put it more bluntly, the inverse tangent of b over a. But this is four quadrant. Good. So why would we use that? Because you notice that when we were talking about our solutions to a differential equation, we had things like e to the 2t cosine of 3t. For one function, I had something like c1 plus c2 e to the 2t sine of 3t. This would be a typical solution to a differential equation that you would have. Notice that if you know what c1 and c2 is, you can rewrite that as e to the 2t times r cosine of omega t minus delta. And from this equation, right, you can pull off your amplitude and your period and your shift. So it's easy to analyze the solution to the differential equation using this technique. Good, I seem to have run out of time already. So in the next video, we'll just do a couple of trig examples.